Hello. Hello. Good evening.
Hello. Good evening. Good evening, sir.
Yes. Good evening and
Yes. Good evening and
welcome to the live interaction session.
welcome to the live interaction.
So it is 7:10 and I'll be starting the presentation now.
Okay.
I hope that my screen is visible. There is some issue with the network. If there is any issue, kindly let me know so that I can switch to another network.
Okay.
Yeah. So today we are going to start the ninth live interaction session. I welcome you all for this NPTEL course on Advanced Reinforced Concrete Design, and the course is brought to you by NPTEL. The course instructor is Professor Surya Prakash from IIT Hyderabad, and today we are in the live interaction session 9, and we are going to start with the topic of columns. And this session is being presented by me. My name is S. Dalit Sagar. I am a doctoral candidate and PMRA fellow in the Department of Civil Engineering at IIT Delhi. And I would just like to start with a brief introduction on this module. So we are dealing with module number 8 on columns. So this module consists of 5 parts in total. So I would just like to give an outline as to what we are going to cover in today's lecture, today's live interaction session, and what we intend to cover in the next session, and what to expect from this particular module on columns. So part 1, we are going to we studied the column types and the determination of the effective length, and in part 2 we have studied the codal provisions and the behavior of short axially loaded columns. So in today's live interaction session we are going to be dealing with the theoretical and the numerical aspects of these two parts, and in the next live interaction session we are going to take up the remaining parts. So the part 3 deals with the behavior and analysis of short columns with axial loading and bending. In part 4 we are going to consider the short columns under axial compression and biaxial bending, and in part 5 we are going to study the design of slender columns, particularly as per the IS code procedure. Okay, so in today's session there are about 16 questions. So without any further delay, I think we can start with the question and answer session. I'm going to skip this summary for today. If there is any questions, kindly let me know so that we can discuss and clear the doubts if there are any. So let me just switch to the other internet network so that our session it can go on without any interruptions. Yes. I hope that my screen is visible.
Yes, sir.
Yes, yeah. So
Yes. Yeah. So
we have the first question.
we have the first question.
Sir, can you
Sir,
kindly
can you kindly
switch off the
switch off the
speaker because I'm hearing an echo. Yeah, thank you.
yeah, thank you.
I'm still able to hear the echo. Okay, now it is fine. Yes. So we have the first question based on the effective length. So as you know, columns is a very crucial part of a structural system. So we are going to start with one or two conceptual theoretical questions. Then we will make our way into numericals. So question number 1 is, what is the correct range of effective length factor for columns in a braced frame and unbraced frame?
Is B, sir.
Okay.
B for boundary.
Okay. Yeah, thank you for the response. So the answer is option B. Option B is absolutely right. So this is the explanation, and it has been taken directly from the lecture slides covered by sir. And so essentially what we mean by braced and unbraced frame is that for a braced frame we are not allowing the columns to sway at the member ends. So we have different boundary conditions, both ends fixed, and here it is both ends bent. So the effective length factor for a braced frame essentially varies from 0.5 to 1.0. However, for a practical case, it is usually about 0.8 to 1. So we'll be looking at the numericals at a later stage. And when we come to the sway frames, essentially we are allowing the member ends to have lateral displacement with respect to the longitudinal axis of the member. And here, as we can see, the effective length essentially varies from L to essentially theoretically it is infinite. So the effective length factor varies from 1.0 to infinity, but practically even for the worst scenario it is going to be 10. So the value of k can be taken as 10. So for an unbraced frame, theoretically or for a sway frame, the effective length factor varies between 1.0 to infinity. So as we can see, option B is correct for non-sway frame and a sway frame, or a braced frame and an unbraced frame. Okay. Moving on to the second question. What is the minimum and maximum longitudinal reinforcement to be provided in the NAVC column as per IS 456? We will take about 45 seconds.
Answer is D. D for Delhi.
Okay, thank you for the response. So the correct answer is option D. So if we look at clause 26.531 of IS 456, so this particular clause mentions that the cross-sectional area of the longitudinal reinforcement, it should be minimum of 0.8% of the gross cross-sectional area and it cannot be greater than 6% of the cross sectional area. So yes, so the answer is essentially it is option D. It cannot be less than 0.8% and it cannot be greater than 6% of the gross area. Okay, so now we will move to the third question. So we are having a numerical problem, and what we are going to do today is we are going to take up this multi-story column within a multi-story building frame, and then we are going to perform the design. So it is going to be an integrated question. So I request the participants to take note of this data so that we can solve the subsequent questions of this particular problem. Okay, so I will very briefly read out the data pertaining to this particular problem and for the subsequent problems also. So we are having a multi-story building. So what we are given here is the plan, the framing plan of the building. So the columns, as we can see, it consists of 3 bays along the global x direction and 3 bays along the global y direction, and the dimensions of the columns are 300 mm by 400 mm, 300 mm along x direction, 400 mm along the y direction, and the longitudinal beams, they are having a size of 250 mm by 600 mm. That is acting they are essentially framing along the global x direction, and the global y direction we are having the transverse beams, and they are of dimensions 250 mm by 400 mm. Further, the story height is 3.5 meter, that is from floor to floor. The floor to floor height is 3.5 meter. So in question 3 we need to determine the unsupported length of this highlighted column about the x-axis and the y-axis. Okay, kindly take 2 minutes and suggest the appropriate answer.
B, Bombay. B for Bombay.
Okay. Okay, just to clarify, I would like to define what is the meaning of this direction. So about x-axis, in the sense, we are essentially looking at the effective length along the y direction. Okay, and about y-axis is we are looking at the x direction. So kindly reconsider the definition and let me know what is the appropriate answer.
Pardon, sir?
I'm sorry.
Pardon? What is the question, sir?
Okay. So what I was telling is that when we are telling the unsupported length about y-axis, about x-axis, so it means that we are considering the length along the y direction. So about y-axis means about y-axis in the sense it is bending along the y direction.
Okay.
Yeah. So please reconsider the definition that is used and suggest the right answer.
So it will become reverse, sir. 3100 and 2900.
Yeah. Thank you for the response.
Okay.
Okay, so we will look at the right answer. So the right answer is option A, and I will just briefly I will give a sketch and I will explain how the answers are coming, so that we are clear about what we mean by the how we are defining the directions, how we are calculating the unsupported length. So okay, so let me take the pen. Yes, so essentially we are looking at this particular column, right? And I mentioned that the story height is 3.5 meter, so it is 3.5 meter and it is essentially from floor to floor. So here we can see we can consider this as maybe first floor, so we will call it as the first floor, and we are going to call this as the second floor, and this 3.5 meter is essentially the distance between floor to floor. Okay, and now if we have to calculate the unsupported length about the x-axis and y-axis, so what I am defining as even in the practice also, how we define the direction is that this x-axis is the major axis, or it is the stronger axis, because if we consider x-axis, so bending about x-axis axis, we will have a depth of 400 mm. So essentially if it tries to buckle about the x-axis axis, it is going to have a higher resistance because the depth is 400 mm. So we have to consider this particular depth when we are we have to consider a depth of 400 mm when the column is trying to buckle about the x-axis axis, and we need to consider a depth of 300 mm when the column is buckling about the y-y axis. Okay, so we have the columns. It is mentioned that the longitudinal columns have dimensions of 250 mm by 600 mm. Okay, so if we cut a section at this point and then we look the section, so essentially this particular beam that we are seeing, okay, so let me just for the sake of this problem, I'm going to name it as kindly bear with the poor handwriting. So just for the sake of this example, we will consider this as CD. Okay, and for this particular beam, the depth of this beam is 600 mm. Okay, and what we are seeing in the cross-sectional view is that we are seeing the beam which is spanning along this direction. Okay, so we can only see its depth, and for this particular beam, it is having a depth of 400 mm. Okay, so whenever we are considering the unsupported length, let me call it LU about x. Okay, so whenever we are considering the unsupported length about the x-axis, okay, we need to consider the unsupported length along the y direction. So when it is bending about the x-axis or along the y direction. So we need to subtract the depth of the beam which is providing resistance to the buckling. So 3.5 meter is the unsupported length. Subtract the depth of the beam, that is 400 millimeter. Okay, so that will be 3100 millimeter. Okay, so this is the unsupported length about y-axis. Okay, sorry, about x-axis. Or it is along the y-axis. Okay, so here I just want to spend some extra time so that moving ahead we are very clear about the nomenclature. Okay, so that is about x-axis. Let me write down in a different color for. So the unsupported length of the column about x-axis is 3100 millimeter. Further, if we consider the unsupported length about y-axis, or along the x-axis, okay, so the unsupported length about the y-axis, so we have the unsupported length minus, so since it is trying to bend about the y-axis or along the x-axis, we need to subtract the depth of this particular column. Okay, so that would be 600 mm. Okay, that would be 2900 millimeter. Okay, so I would like to reiterate this concept once again, this terminology. So whenever we are considering the effective length about x-axis, it is going to be along y-axis. So whenever we are considering bending about the x-axis, we will consider the length along the y-axis. Whenever we are considering the buckling about the y-axis, we are going to consider the effective length along the x-axis. Okay, so with that clarity, we will move on to the next question. So it is essentially a series of questions. So for the multi-story framing plan given in question 1, we need to determine the cumulative stiffness of the columns along the x and y axis. Okay, so kindly pay attention to the terminology. So we are looking at the cumulative stiffness along the x-axis and along the y-axis. So what would be the cumulative stiffness along the x and y-axis only for the columns? Okay, kindly take 2 minutes and let me know what would be the appropriate answer. So please remember, we are considering only for the columns, and the stiffness for one column, it is given by this expression, IC by HC, that is the moment of inertia divided by the height. So this particular height would be the floor to floor height. Okay, so that is one more hint that I would like to provide. So here HC would be So we will find the stiffness of the column for one column, and then we are going to multiply by the number of columns. Okay, so kindly take 2 minutes and let me know what is the correct answer.
ये
Okay. Okay, sir. Like here again, the terminology is slightly different. I would, request you to check once again. So it is along the x-axis and along the y-axis. I think you're almost there. Just
I will not catch.
okay. Okay, so I think let us see, what is the answer. I can understand actually it is the terminology is a bit confusing, but I will try my best, to make it clear. So I have just considered this. Okay. Okay, just erase this part. Okay, so I'll take up a different color. And yes, so essentially we are determining the cumulative stiffness of the columns along the x-axis and along the y-axis. So as I was mentioning, along the x-axis means about the y-axis. Okay, so we need to consider so we will do the summation for all the columns later on. So we have Okay, so we have 400 into 300 cube divided by 12. Okay, so that is for one particular column along the x-axis. So along the x-axis means about the y-axis, which is why I have considered. So the moment of inertia is bd cube by 12. So b is 400 by 300 cube divided by 12 divided by, so IC by HC. So HC would be the story height, floor to floor story height. So I'm going to consider that is 3500. Okay, and that I'm going to multiply by 16 because we are considering the entire floor. So there are 16 columns altogether, and the dimensions and the orientations of the columns are the same. So when we perform this particular calculations, we get a value of 4114 into 10 to the power 3 millimeter cube. Okay, so yeah, the option B is the right response. So when we consider along the y-axis, so along the y-axis means about the x-axis. So along means we have 300, again bd cube by 12, b is 300, d is 400 cube by 12. Okay, by IC by HC. HC is the same. We are considering the floor to floor height. Again we are going to multiply it by 16, for which I got a value of 7314 into 10 to the power 3 millimeter cube. Okay, so option B was right. Again, I think I request you to be mindful and be patient regarding the terminology whenever we are using about and along. So this would be the cumulative stiffness of the column along the x-axis and along the y-axis. So along the x-axis is 4114 and along the y-axis it is 7314. Okay, so the next question is, we need to determine the cumulative stiffness of the beam along the x-axis and along the y-axis. Okay, so kindly take 2 minutes and let me know what would be the correct answer. So again, the hint is that the stiffness of the beam is IB by LB. Okay, so we have, let me use, okay, summation of IB.
B means longitudinal beamness, so this is not transversal.
Yeah, yes sir, I mean for the x direction you have to consider the longitudinal beam. Okay,
No, not that one. Two beams are there in this.
yes, yeah, so the longitudinal beam, it refers to this one, 250 by 600.
Okay.
Okay, and the transverse beam refers to this. So for the x direction we need to consider this beam, and for the y direction we need to consider this beam. Okay, so I was about to actually draw the cross section now. I will make this capital X because we are dealing with the global x direction. Summation IB by LB respect to y. Right, let me draw the cross section.
Answer is E for elephant.
Okay, thank you for the response. Yes, we will start solving the problem now. So this would be 400. Okay, so we will start the solution. Right, so as I was mentioning earlier, we need to consider the moment of inertia, and it is BD cube by 12, that is 250 by 600 cube divided by 12. I'm going to write it this way, and LB, and if you consider the spacing of the frames along the x direction, so it is having a span of 6 meters. Okay, so let me write here 6 meter, and there are 12 beams, okay, along the x direction. So if we consider there are 12 beams, so 1 2 3 multiplied by 4 frames along the x direction, so 3 yes, let me write here 3 by 4, that is 12. So we have 12 beams along the x direction, along the global x direction, as well as 12 beams along the global y direction, because 1 2 3 and 4 frames, so we have 12 along the both x as well as y directions. So moving on, yes, so when we simplify this, we get the value of 9000 into 10 to the power 3 millimeter cube. Similarly, for the beams that are spanning along the transverse direction, we have 250 by 400 cube divided by 12 divided by, so what is the span along the transverse direction? So the span is 4 meters, as we can see here. Okay, I'm sorry, this has to be 6000, this has to be 4000 into 12, because there are 12 beams along the transverse direction. So the cumulative stiffness here would be 4000 into 10 to the power 3 millimeter cube. Okay, so among the options we have option E. Option E is definitely it's the right answer. So congratulations, and we will move forward to the next question. So in this in the earlier questions, first we found out the unsupported length. Let me just write it here. First we found out the unsupported length, that is LUX and LUY. Okay, then we found out the cumulative stiffness, sigma IC by HC and sigma IB by LB. So in this question we need to determine the lateral flexibility, okay, that is given by delta U by HU, that is story drift per unit story shear of the story along the longitudinal and the transverse direction. So longitudinal, we have to find out along the longitudinal and the longitudinal x direction and the transverse x direction, that is y direction. So we can actually use the data that we found out from the previous question. Okay, so as a hint, I am just going to write down the formula. Kindly take 2 minutes and let me know what would be the appropriate answer. So as I was telling, each question will give the data for the next question. So we are solving an integrated problem today. So we have the equation for lateral stiffness, that is delta u by hu. So lateral stiffness is nothing but the ratio of the story drift by the story shear. Okay, that is given by h square. Okay, kindly take the help of this particular equation and let me know what would be the correct answer. Okay, so we need to determine the value of this lateral flexibility along the x-axis and the y-axis. Okay, so we have to use the modulus of elasticity of concrete. So we have elasticity of concrete as, okay, let me utilize this space here. EC column is equal to EC Okay, I'm going to start putting in the variables.
3A 1.3.
Okay, okay, sir. You mean option A is the right answer? Okay. Kindly check your calculations once again. Okay, I'll be putting the options so we can anyway verify. Again, kindly take this into consideration. Here HS stands for the floor to floor height. Okay. Okay. Can I go ahead with the answer?
Yeah.
Okay, okay, sir. Fine. So ultimately, when we solve this, so the correct answer is option D actually, because when we simplify this, we get 1.5 into 10 to the power minus 5. Oh, I'm sorry, here I should have written into 10 to the power minus 5. Okay.
I am getting 1.258 actually.
Okay. Have you taken the correct value of HS?
Yeah, sir, 3,500.
Okay, okay. Okay, sir. I will check my calculations once again. Okay, but okay. I am getting 1.5. So kindly, I request the participant and also people who are watching the recording to check it once again. So we will move ahead. We can verify this later on, but for the subsequent problems, we are going to take this value. We are going to consider this value and move ahead. Okay. So please take down this particular value. So the lateral flexibility, that is delta u by hu, along the x-axis we are going to take a value of 1.5 into 10 to the power minus 5 along x-axis, and along y-axis we are going to take a value of 1.7 into 10 to the power minus 5. Okay, I will make the modifications in the final PPT that you get. Okay, let's consider these values and proceed forward.
Okay.
Yeah, so this is the equation that we considered in the previous slide. So for the multi-story plan, so determine the stability index along the x-axis and the y-axis. Okay, so again we need to consider the stability index along the x and y direction. So what do we mean by stability index? So the hint given here is that, so the stability index corresponds to, which is given by q, the equation is given by summation of pu divided by hs into delta u by hu. So this flexibility coefficient we found out in the previous question, and here delta pu corresponds to the sum of actual loads on all the columns for the story that is considered. So that is given as 7560, and here hs corresponds to the floor to floor height. Okay, so kindly take 2 minutes and let me know what is the stability index along the x direction and y direction. I will start writing the equation. So we will consider so we are still at the global level, so I am performing all the calculations with respect to the global x-axis and global y-axis. Okay, right. So we have to maintain the uniformity of the terms. Okay, I'll take another color for contrast. So we have the flexibility coefficient in terms of millimeter and Newton, so I'm going to maintain that same units, 75 10 to the power 3 by 0 0 2. Let me write it out here also. So along x-axis I found that it is 1.5 into 10 to the power minus 5, which will give us the value, and here it is 1.7. Yes, 1.7 into 10 to the power minus 5. So do we have the answer?
Three 0.032.
Yes, yes. And for the y-axis? Yes, I hope you're getting the answer.
Point 0.027.
0.037, right? Yes. Since it is this is 1.5 and this is 1.7, this has to be the stability index along y has to be greater than x. So option C is the right answer. Okay. So yes, before proceeding further, I would like to add something on the stability index. So this is the equation for stability index, and based on the ACI code, if q, the value of q is less than 0.05, so we are going to consider it as a braced frame or a non-sway frame. It would be a braced or a non-sway frame, and if it is greater than 0.05, it would be an unbraced or a sway frame. Okay, so this is going to help us in the next part of the question. So we have to consider the highlighted interior column and determine the effective length about the major and minor axis. So again, I would like to bring to your notice that we have switched the terms once again. So kindly find out the effective length about the major axis and the minor axis of the column. So again, just to refresh our memories, we are dealing with this particular column. So we have decided that since the stability index is less than 0.05 along both the x and y direction, so it is a braced frame, and we have to find out the effective length for this column. So if we look at the annexure E, we will have the procedure in order to determine the effective length. So earlier we have found out the unsupported length, and then we found out the buckling length. So now we need to determine the effective length about the x-axis and the y-axis. So I will start writing the solution here so that we can Okay, so I've started to solve the problem. Let me call it as, just because beta 1 is equal to beta 2, I'm just going to consider beta, that is since all of it is raised to the power 10 to the power minus 3, I'm just going to drop this 10 to the power term. So I got a value of 0.733. Okay, so I hope okay, should I okay let me just I will go ahead and then I will explain the calculations. So yeah, so I'm getting a value of 0.733. So we have, for a column in a frame with no sway, we have the values of corresponding to the values of beta 1 and beta 2. We can find out the k factor. So we have the k factor of as 0.733. okay, so let us see what we will get. So 0.733 comes somewhere around here for beta 1 and for beta 2 also. For so the value lies between 0.8 and 0.85. So I'm going to take a point somewhat here. Okay, so let me just mark it corresponding to, again it can be a little bit subjective, so whenever we have a doubt we can take slightly on a conservative side. Okay, so we need to mark out corresponding to beta 1 is equal to beta 2 is equal to 0.733. we need to drop perpendiculars from here, 0.733. okay, and here 0.733. I'm going to drop a perpendicular corresponding to those points. Okay, and I'm going to choose a value of 0.82. okay, okay, so I'm going to just go back to the calculations. So we need to in order to obtain the k factor, that we need to multiply with the effective length. Okay, so before that I'm going to write down the value of k here. So k is 0.82. so L effective x is given by 0.82 multiplied by the unsupported length along the x-axis. So that was
310.
yeah 3100. yes, thank you. 3100, for which we get a value of 2542 millimeter. Oh, I'm sorry, I didn't modify the options here. (2542 millimeter). Okay, I'm sorry for that mistake. I should have checked it once again.
So number of joints is 2, na? Because it is single column, it is 2.
Yeah, yes sir, yes, you're right, because
If it is double storage,
I mean I will explain what exactly we are doing. Like, we are considering the joint over here, so we are considering this particular interior joint. So we need to consider how many members are meeting. So if we consider this joint, so we have one column that is going up and one column that is going down, isn't it, sir? Hello?
It is plan, sir. It is a plan.
Yes, it is a plan. So one column is going up and one column is going down. So we need to consider two columns, and when we consider each direction, there is one beam here, one beam here. So when we consider global x direction, there are two beams. When we consider global y direction, there are again two beams. So which is why, we are taking that.
The column is single, sir. How it is two?
No, like whenever there is a joint, we are taking it as a separate column. Okay. So imagine this is a floor.
So it is a single floor, no? Single floored building. Okay.
Yes, single floor only, but there are two columns, sir. Like if you consider this as a let us say that this plan is at the first floor. Okay, so there is one column that is going to the second floor and one column that is going to the ground floor.
Even though second floor is not there, first floor is not there, we have to consider.
Yeah. So it is a multi-story building. We are considering only one particular floor plan.
Okay. Multi-story elements.
Yes,
okay,
yes.
thank you.
Yeah. So if we take this one, let us if we assume this as a first floor slab, so there is one column going to the second story and one column that is going to the ground floor. So we need to consider two, and for each of the horizontal direction we will consider two beams. Okay.
The number of columns meeting at joint and the number of beams meeting at the joint. Okay.
Yes, exactly. So since it is an interior joint, there is two, which is why we are going to multiply here. When we consider the columns, we are going to multiply it by 2, because there are two columns meeting at the joint and there are two beams meeting at the joint. However, if you take a different, like if you consider a corner column, then it is going to vary. For example, I'll just tell you very quickly. If we are considering this particular column, let's say this particular joint, then if we consider the column is going to remain 2 only, but if you consider the beam, then along the x direction you are going to consider only one beam, but along the y direction we are going to consider 2. And if we consider this corner joint, then we will consider one beam each along both the x direction and y direction, and two columns for this particular column joint.
Okay.
Yeah. So thank you for that question. So which is why we are taking this number.
Yeah, it is actually not explained anywhere.
Yeah.
Thank you.
Yes.
Thank you.
Thank you. So when we do that, we get this value, summation of IC by HS, IB by LB. Then when we substitute this in this equation for beta 1 and beta 2, so here it is 0.5 for a sway for a non-sway frame, and for a sway frame we need to consider it as 1.5. So it is provided in the annexure E only. So when we substitute that, we get the value of beta 1 and beta 2, both will be 0.733. So when we consider this chart from annexure E, we saw that for 0.733 we have the value of K, effective length factor, as 0.82. We took it as 0.82. When we multiply 0.82 by 3100, we get a value of 2542. Again, I'm sorry about this. I'm going to modify this when I upload it in the Google Drive finally. And when we consider since we are running short of time, I'm just going to give the values for the calculations about the y-axis. So for the y-axis I got a value of ky would be ky would be 0.64 and then ley would be 0.64 into 2900, so that will give us a value of 1856 millimeter. So I request you to take this as a homework and just verify that you are getting this as the right answer. Okay, so we have determined the effective length along the about the x-axis and the y-axis. So the next question is, we are going to design the column. So for that, the question here is, we need to determine the slenderness ratio about the x-x axis and the y-y axis. Okay, kindly take 1 minute and let me know what is the right answer. Okay, so what is the value of the slenderness ratio? Would you like to volunteer?
.47 and 6.18.
Okay, I think there is a slight confusion. I think
It is 215 and by 400.
yeah, because we
Minor
are
axis.
about we are considering about. Okay, sir. So that is, I think. So if we consider about, then it is actually along. About x-axis means along y-y.
But least lateral is always same, na sir? It is.
I'm sorry.
Least lateral dimension means it is dx dy. It is okay.
Yeah. So we are. I think that comes later. When we are for the eccentricity. So I know that this is very confusing, but I think conceptually, if we are clear, we can understand. I know that even in when we refer different textbooks also, and even in sir's lecture also, the notation there can be little non-uniformity, but once we understand the concept and actually get a feel for how the structure is behaving or how the column is buckling, then we can actually solve it irrespective of the notation. So again, I request you to kindly get adjusted to the notations that we are following for this session. So here what the question is asking is that you have to determine the slenderness ratio about the x axis. So we calculated that the effective length about the x axis is 2542 divided by 400, because about xx means along yy, so that depth about xx would be 400 millimeter, so that is 6.36. okay, and here effective length about yy axis is 1856, and the depth about yy means along xx, so that is 300, so this would be 6.19. and how should we classify and design as per the IS 456? Since the slenderness ratio about both the major and minor axis are both less than 12, so both of them are less than 12, slenderness ratio, so we can go ahead and classify it as a short column. So option C is the right answer. So we will take up the design from the next question forward. So we will design it as a short column. Okay. Yes. So the compression member may be considered as a short column when the slenderness ratio are less than 12 about both the axes. Okay. So let us proceed to the next question. So for the interior column that we saw in the previous question, so this has to be question 9. Sorry. So question 9. What should be the minimum eccentricity about the xx and yy axis? Okay. So this is nothing but so here I request you to take the unsupported length, okay, not the effective length. Okay, this has to be not 300, it has to be 30. I will start substituting the values. If you get the answer, kindly let me know the correct answer. So L here is okay. So I got a value of 19.5. So this minimum eccentricity, it has to be either this L by 500 plus dx by 30 or 20 mm, whichever is greater. So I am going to consider this value, and again eccentricity about y-axis, L is 2900 divided by 500 plus 300 by 30. I got a value of 15.8 and 20 mm. So it has to be the greater of these two values. Okay, again greater of these two values. So I am going to consider the minimum eccentricity of 20 mm along both the x-axis and the y-axis. Okay, so though we get values of 19.5 as per this equation, the minimum value has to be 20 millimeter. So I am taking this value, and when we consider about the y-axis also, as per this equation we are getting 15.8, but the minimum eccentricity has to be 20 millimeter. So I am taking this value. Okay, so the correct answer is option D. So yeah, this is exactly what I was trying to say. So we need to determine those both these values, L by 500 plus D by 30, L by 500 plus D by 30, and 20 millimeter. So whichever is greater, we need to take this value. So accordingly I have taken the value of 20 millimeter and 20 millimeter. Okay, so we will move to the next question. So this has to be question 9 once again. Sorry for the typo. I made some modification to the PPT, which is why the change of question has not been reflected. So the question is, when this particular interior column is subjected to a service load of 1500 kilonewton, determine the area of longitudinal reinforcement required as per IS 456. So we need to determine the area of longitudinal steel, and we need to consider the material properties as M25 and Fe415. Okay. So we have the design of axial members as per IS 456. We have this particular equation, that is Pu is equal to or this equation can be alternatively written as so here let me break down what is the meaning of each term. So this is the factored axial load, and FCK is the strength of concrete, and area is the gross area. that is 300 by 400 as we have seen for the column, and Fy is the yield strength of the steel reinforcement, FCK is the grade of concrete, and AAC is the longitudinal reinforcement. So we need to determine this particular value. Okay, so let me start plugging the variables here. So I'm going to take a different ink for better contrast. So here I'm given the service load is 1500 kilonewton. So in order to obtain the factored load, I'm going to multiply it by a factor of 1.5, that is 1500 into 1.5, so that is 2250 kilonewton. So I request the participants to just start solving with me and let me know the answer if they are able to solve the problem first. So all the terms are right in front of you. So upon solving this equation, I am getting a value of, I'll wait for 15 seconds if the participants would like to answer. So I got a value of 3918 mm square. Okay. So option C is the right answer. So before providing the longitudinal bars, I'm going to just check for the minimum reinforcement criteria. So the minimum reinforcement criteria is 0.8 times 0.8 percent of gross area, that is 0.008 into 300 by 400. So that is nothing but 960 mm square. So since the value of AAC is much higher, and we can go ahead with this. So I tried for let me write the reinforcement here. So 8 of 25 bars, 25 mm diameter bars. So in that case the AAC provided would be 3927 mm square. So since it is slightly just marginally higher when compared to the AAC required, I prefer to provide 4 of 28 diameter and 4 of 25 mm diameter. Okay. So in this case the AAC provided would be 4426. So I would like to check if this is exceeding the maximum permissible reinforcement also. So the maximum permissible reinforcement, I'll take a different color for better contrast. So that would be 0.06 into BD. that would be so that would be 70 to 100 millimeter square. So I prefer to what we have provided by using 4 bars of 28 mm diameter and 4 bars of 25 mm diameter. So the AC provided is much lesser when compared to the limiting reinforcement. So we can go ahead with this longitudinal reinforcement configuration. Okay, so coming to the next question. So the next question is we need to determine what is the diameter and the spacing of lateral ties that is both structurally safe and economically efficient. Okay, so I request the participants to solve the problem along with me. So as per the IS code provisions,
Answer is F, sir.
okay, F. Okay, thank you sir for the response. So I'm going to provide the step-by-step procedure very briefly, because yes, answer option F is absolutely right. So just for the sake of completeness, I'm going to provide the solution. So first we need to fix the diameter. So as per the IS code, for the lateral ties for the column that is subjected to pure axial loading. So let me remind you that the equation that we used earlier, so this is for the pure axial loading. Okay, so here there is a clause that the minimum eccentricity should not exceed 0.05 times the lateral dimension. So we consider 0.05 into 400. Okay, so this 20 mm, it is almost close to the minimum eccentricity that we considered.
It is equal.
Yeah, so it is equal. So the minimum eccentricity, so whatever we calculated, Ex minimum and Ey minimum, so this should not exceed this 0.05 lateral dimension B or D. Okay, so in that case, since it is almost equal to it is the same as 20 millimeter, we can go ahead with this. Okay, so this is the equation for purely members that are subjected to pure axial load. Okay, so whenever there is a moment, we are going to deal with in the next chapter. So this is only for pure axial, or the eccentricity is within this prescribed limit. But whenever there is axial plus bending, we are going to design them as per the PM interaction curves, so that we are going to deal in the live interaction 10. Okay, it is the next week. Okay, so we have designed the longitudinal reinforcement. So now we are looking at the design of the lateral ties, right? We are looking at the design of lateral ties. So the diameter has to be firstly uh, the diameter of the bars, the diameter of the maximum bar, that is 28 divided by 4, so that is 7 millimeter. So, and the second, it has to be minimum of 6 millimeter, right? So we have to provide whichever is higher between these two. So we will consider 8 millimeter diameter bars. Okay, then the spacing. So the spacing has to be the minimum of these three values, that is 450 millimeter or 16 times the least diameter of the longitudinal bar, that is 16 into 25, that is 400 millimeter, or 300 millimeter. Okay, so whenever we are providing the diameter, so this has to be the highest of these two values, but when we are considering the spacing, so we have to provide the least, so or the lowest value. So we can safely provide for this axial member, we can provide 8 diameter at 300 mm center to center. Okay, so I am going to just provide a sketch very briefly. Yeah, this is what I was telling. So the among the longitudinal bars provide the maximum. So in our case maximum is 28, right? Let me draw the sketch so that it becomes clear for us. I'm going to draw a sketch now. So here is the column that we considered, 300 in, along the global x and 400 along the global y. So we are providing 28 millimeter bars along the exterior, the corners. Okay. So this shading is just to highlight that it is 28, and I'm going to provide 25 in the middle, right? Then we are going to enclose them using the lateral ties. Okay, so one option here is that we can provide staggered ties. So one can be this way, and one can be in a diagonal fashion like this. Okay, it has to be straight. Excuse me for my poor drawing. So this has to be 4 bars of 28 diameter at the corners. Kindly make a neat sketch of it in your notebooks. And this has to be 4 bars of 25 mm diameter at the side face. Okay, and we can provide a staggered reinforcement. I'm going to mark it like this, that is 8 mm diameter at 300 center to center, and it is staggered. That is if one lateral tie is in this rectangular shape, other can be in the diamond shape. Okay.
So why diamond shape is required in it?
So that is only to provide the provide a better confinement for this, because this rectangular shape, it will provide confinement to these corner bars. Okay, and this diamond shape, it is going to provide a special focus for these side face bars. Okay.
It is always required. Huh?
No, it
If
is
we want to provide any
it is not necessary.
reflection.
It is not necessary, it is just we can provide.
More references.
Yeah, yes. Yes, so that is the design of that interior column that we started from question number 1. So if we remember, we'll keep the annotations. So we started at 710 with this particular problem. So we found out the effective length, found out the we found out the unsupported length, then the whether it is a sway frame or a non-sway frame. Then based on the IS code we determined the effective length, and then we found out the slenderness ratio. Then we decided based on the IS code whether we need to design it as a short column or a slender column. Then we designed it as a short column, and ultimately we found out using the annexure E, the charts, we found out the effective length, then slenderness ratio, ultimately the longitudinal reinforcement, then the lateral ties. Ultimately we came to this the design. Okay, I request you to make a neat sketch in your notebooks. Okay, I didn't prepare a very neat sketch here. So that was the detailed problem. Now we are going to design a circular column which is having a helical lateral ties, okay, which is having a spiral lateral reinforcement. So we are going to solve that problem now. So that has 4 components. So I request the participants to bear with me for another 15 minutes. Okay, we are going to wind up at around in 15 minutes. Before that, we are going to take up one more design problem. So it consists of 4 parts. So in the first part I am going to read out the data. Kindly take a few minutes and let me know the answer. So we are having a circular RC column which is having a diameter of 400 millimeter, and it is part of a braced frame, and it is unsupported over a length of 3.4 meter. So its unsupported length is 3.4 meter. So the question is to find out the slenderness ratio for this particular column. Okay, and we may take the highest K factor for a column in a braced frame. Okay, so based on the slenderness ratio we need to comment whether we have to design it as a short column or a slender column as per IS 456. Okay, kindly take 2 minutes and let me know what would be the appropriate answer. So what would be the slenderness ratio here?
8.5.
Yeah, thank you for the response. So since this slenderness ratio is that is LE by D is less than 12, so we can go ahead and decide it as a short column. So the correct answer is option E. Okay, so we'll proceed to the next question. So for this particular question, what is the minimum design eccentricity? Okay, so it is a circular column. We don't have to find out along the two principal axis, the major axis and the minor axis. So we have minimum is E minimum is unsupported length by 500 plus the column depth divided by 30. Let me take a different color. We have seen that the unsupported length is so it has to be either this or 20 millimeter, whichever is greater. Okay, let us solve for this, substitute these values and see what we get. 3400 by 500 plus 400 over 300, so we get a value of, I got a value of 20.1 millimeter. We have to take the highest of these two values, so we can take that E minimum is 20.1 millimeter. So the correct answer is, as you already know, it is option C. Okay, so now we need to check for this provision, whether this minimum eccentricity is exceeding 0.05 times the lateral dimension or not. So we have E min is equal to 0. It is 20.1 millimeter. Now we have 0.05 D is 0.05 into 400, that is 20 millimeter. So since E minimum is approximately equal to 0.05 D, so we may go ahead and design it as a axial column. So the moment can be ignored. So the moment can be ignored. So this particular equation is going to be applicable.
But slightly more, no, sir.
Yeah, slightly more, I agree, but we can take up, if we are so concerned, then we can, again we have that, we can make use of the PM interaction curve. So
it is safe to go for PM interaction curve.
yes sir, yes, that is definitely, it is true. Yeah, so what I should have done is I could have taken slightly higher value of the diameter, right? So instead of 400, if I had taken 500 millimeter, right? So
Then it will come within limits.
yeah. So I'll take a different color, just since you asked the question, I don't want to leave it hanging, because others who are watching, they might get a doubt. So 0.05 into 500, so that would be 250 millimeter, I'm sorry, 25 millimeter, right? So that would be 25 millimeter. So the minimum eccentricity, again we need to go back and do the calculation here. Yeah, let us do that iteration and see what we are getting, right? So since we are already L by 500 plus L would be 3400 plus 500 by 30. So here it should not be 300, it is 30. So what am I getting? Minimum eccentricity.
23.4.
Okay, yeah, 23.4 millimeter, right? So yeah, so 23.4 when you compare with this 25, so definitely it is 23.4 is not exceeding this value. So yeah, E min is not greater than this 0.05d, then we can definitely we can we can close our eyes, we can go ahead with this thing. But for the sake of this example, let us proceed with this. But yeah, thanks for bringing that up, because as engineers we should always be careful to follow the provisions. So let us assume for this particular example that we will assume that this particular equation is valid, and let us determine the longitudinal reinforcement when it is subjected to a factored load of 1500 kilonewton. Okay, so kindly take 1 minute and let me know what should be the right answer. So we have all the values here except the values of AAC, so we need to determine AAC. So it is quite straightforward. I hope you can obtain the answer. M25 25 into AG is okay. Pi t square by 4. Five just be Fy, right? So did we get an answer?
It is factored is 1500 we have to take, sir, actually.
Yes, sir. So you have to take a factor. If you are given a service load, you can you have to multiply by 1.5, but if it is straight away given as factored, so we can take that only. So I am getting a value of 642 millimeter square. So I request the participants to check if they are also getting this value. So we are going to compare this with the minimum and maximum reinforcement.
906 I am getting actually.
90 is it?
Yes, sir.
Okay, let me check.
0.4 into 2022. Yes.
Okay, I will check it once again. Maximum AST.
It's
Okay, let me solve. Okay, yeah, I think I had made a mistake. I made a calculation mistake. So, yeah, as you pointed out, ASC has to be, yeah, thank you for pointing it out.
1104 total.
Yeah, so that is 907. Yeah, thanks for pointing it out. So we will provide the AC required is 907. Yeah, I made a calculation mistake somewhere, so it has to be 907.9 millimeter square. So when we consider this AG, that is pi by 4 into 400 square into, so the minimum AST has to be 1005 mm square, and let us see the maximum is so I am getting the maximum as 9540 mm square. Okay, so anyway, this AAC required is less than the minimum steel, so we need to provide a minimum steel of 1005.3 millimeter square. So yeah, this option is wrong, so 1005 it has to be provided. So I will make the necessary modification in the presentation that I am going to upload. So now let us see what should be the longitudinal reinforcement that needs to be provided, right? So we have the longitudinal reinforcement. So if I consider 16 mm bars, so 1005.3 divided by pi by 4 of 16 square. Okay, let me so I'm getting a
537.
yeah, I'm getting a value of 5. So but for a circular column with
Minimum 6.
yeah, we need to provide a minimum of 6 bars, right? So I'm going to provide a minimum. Let me draw the cross section. So I'm going to provide 6 bars minimum, right? 2, 3, 6. Okay, pardon me for the poor drawing, but Yes, we need to provide 6 bars of 16 mm diameter. So this would be the lateral ties. diameter. So I am going to provide 16 mm diameter bars, 6 number of them. So the next part of the question is to determine the minimum spacing that should be provided given that we are using spiral lateral ties of 6 mm diameter. Okay, and yeah, we are going to assume a clear cover of 40 millimeter. Okay, so I'm going to start solving the problem here. So the diameter of core would be 400 minus 40 into 2, that is 320 millimeter. Okay, now
Spiral die not required, sir. Cool.
okay, no, it is required. So we have the ratio of the spiral reinforcement as volume of spiral reinforcement divided by the volume of core concrete right. So the volume of spiral is given by the area, the cross sectional area, that is pi into 6 square divided by 4 into the perimeter. Into the perimeter is nothing but
So what is 6? 8 mm, right?
no 6 millimeters, sir. The dia of the spiral, that is 6 millimeter into pi into 320 minus 6. So this would be the area. Let me take a different. Okay, I will finish this. Okay, so let me explain the terms here. So here this would be the area of die, and this would be the perimeter. So we are considering, pi into I will make a sketch here. Sorry for the poor diagram. So here if the overall diameter is 400, right? So the diameter of core given by DC, that would be 400 minus 2 into 40. So that is equal to 320 millimeter. So when we consider the perimeter, we need to subtract the width of the thickness of this tie. Okay, so that would be 320 minus 6, that is 314 millimeter. So these three terms we are using, so just please be careful while we are substituting. Okay, and this is the core, this is the core area, and this is the spacing between the ties. Okay, so when I simplify this, I got a value of rho s is equal to 0.3468 divided by ST. So because of the paucity of the space here, I'm going to continue the next slide. So the rho s is equal to 0.3468 divided by ST. Okay, further, this is, we have rho s should be, so the percentage of this spiral reinforcement should be greater than or equal to 0.36 into AG by AC minus 1 into FCK by Fy. Okay, so AG is, I'm going to calculate AG here. So AG is pi into 400 square divided by 4, and AC is pi into 320 square by 4, right? So I'm just going to quickly calculate that. Pi by 4 into 400 square. .664 mm square, right? And 80425 mm square, right? So when I plug it in this equation, rho s should be greater than equal to 0.36 into AG by AC minus 1 into, what is the FCK we have? FCK is 25, right? Yeah, 25 and 415. Sorry, 25 by 415. So I got this value as rho s should be 28.4 millimeter. I'm just going to check it once again into okay. I need to substitute this. I'm sorry, no, I think I can continue here. So rho s is, I know that rho s is yes, yeah, I know that rho s is 0.3468. so I substituting, I get ST is nothing but 0.3468 3468 divided by 28.4, right? Which no, I'm sorry. Oh, okay. So this I got a value of, just going to take a different color, 0.012, 0.012. Okay, so here when I substitute as 0.012, I got a value of ST is 28.4 millimeter. So the minimum spacing that should be provided, ST has to be greater than 28.4 millimeter. Now in addition to this, the pitch value has to be between these two values. Okay, so it has to be either 75 millimeter, okay, or core diameter, that is 320 by 6, that is 53.3 millimeter, okay. Further, it has to be greater than either 25 millimeter or 3 into 5t, that is 3 into 6, that is 18 millimeter. Okay, so ultimately the value of ST, we have this 28.4 millimeter, and also as per the IS code provision, so it is as per clause this clause 26.5.26.532D. okay, so ST, it has to be, ST has to be greater than this 25 millimeter, and it has to be less than 53.3 millimeter as per our calculations using this these conditions. Okay, so
3 times diameter, sir?
yeah,
3 times diameter steel?
yes, so this 5t corresponds to the diameter of the lateral ties, so we have taken it as a 6 millimeter. Okay, so when we combine these two clauses, so we can say that since the spacing that we calculated is 28 is within this range, so we can go ahead and say that ST, the spacing of ties has to be 28 millimeter. Okay, so that is the correct answer.
So 3 times 6 is 18 also, no, sir?
Yeah, yes sir. So
So 18,
so it has to be greater
not
than,
less.
it has to be greater
Oh,
than,
not less than 18. Okay.
yeah. So again we have 25 millimeter and 18 millimeter, so it has to be greater than this value. So yeah, so we have to provide within this range. So the spacing should not be less than 25 millimeter, or it should not be greater than 53 millimeter. Okay, so the spacing that we calculated, if it was less than 20, let's say we got 23 millimeter, so in that case we had to provide a minimum of 25 millimeter, or let's say that we had got 55 millimeter, in that case we had to provide 53 centimeter. So since the calculated value is within this range, we can go ahead and provide this value to resist the given axial load. Okay, so we will go ahead and complete the diagram. So we have seen that for a 400 millimeter diameter circular column, we need to provide 6 bars of 16 mm diameter, and we can provide a spiral reinforcement of 6 millimeter diameter at a spacing of 28 millimeter center to center. Okay, and this is a spiral. Okay, so this is the final diagram of the column. So with that, we have come to the conclusion of this session. So
But it's very difficult method with 20 mm aggregate of concrete. If we provide this 25 mm.
yeah, yes sir. So
28.
yeah, so whatever calculation we have done, that is corresponding to 6 millimeter. So definitely sir, if we provide 8 millimeter, we can increase the spacing.
So related to aggregate, there is no any relation, sir.
Yeah,
So even if
yes
25 mm comes, then we can provide no problem. If 20 mm aggregate we are using.
yes sir, but 20 mm, again the thing is
Because in
with helical reinforcement, if you reduce the diameter, then it is highly effective. So again, if it is required, we can if it is possible to provide 20 millimeter aggregate, then we can definitely go ahead and provide this one. But if you say that no, if the aggregate size is 25 millimeter and more, then we can always go for 8 millimeter, because remember that as we are increasing the diameter of the spiral reinforcement, then bending them into circular shape also becomes difficult.
But this concrete will not come out of helical reinforcement, no, sir.
Yeah,
We are
so
using 20 mm aggregate. Within
yeah,
25 mm, it won't come for cover purpose. The concrete also come outside that helical reinforcement.
yes sir. So in that case, we can where there are two options. We can go for 8 millimeter diameter. We can twist them into helical reinforcement, and in that case, definitely this spacing is going to go up. So you can actually
There is no other option. Only 6 mm or 8 mm. That's all.
yeah, because 10 mm, it becomes very difficult. So
No, maintaining 6 mm, we cannot adjust anything. No?
no,
Keeping 6 mm diameter of helical reinforcement, we cannot adjust pitch.
no sir, no, because if we want that helical action, no, then we have to stick with this spacing only. But I suggest that
So the chances of honeycombing, so much of honeycombing in practical.
So this is for the purpose of calculation we took it up. But what you can do is, you can, as a homework, you can try 8 millimeter diameter. Then maybe next class, when we start the session, even I will also do the calculation. So then we can discuss.
So practically I am asking, sir. Okay, 8 mm is okay, next option. Keeping 6 mm, we cannot do anything.
Exactly.
Keeping
So
6
yes sir, so if I am designing, if I am designing the column, then definitely I will see, I will go for 8 millimeter dia.
for
Then
practical purpose.
then I will see, then definitely it will go up, and it is good. Like it is 8 mm diameter is workable also, and then there
No,
won't
they are
be,
using 8 mm also.
there
Yeah.
won't be any honeycombing, as you said. So I think
In
that
piling, generally 8 mm they will use. 10 mm also they are using in piling. Yeah.
okay, oh, that is nice, to know. So yes sir, so we can actually consider 8 mm and 10 mm dia, then we can see how the spacing will vary.
If 30-40 mm comes, then it is safe for aggregate concrete.
So this is
Right. Okay.
again from
Mm.
a theoretical perspective I took, but definitely as a design engineer, you can uh, always consider 8 mm dia and 10 mm dia spiral bars. Then we can see how it is improving the spacing. Okay, thank you for that input. So with that, I'd like to conclude the session. So thank you for joining. So we will meet again next week, same time, with the second part of the column lecture. Okay.
So finally, any model will be explained, one frame model. I think one, two story or three story.
No, sir. I don't think it'll be explained, because in module for the live interaction session we are having the serviceability module, and for 12th live interaction session we have the slabs. So I don't think we'll be dealing with that. So yeah, if you would like, you can drop a mail in the group, then sir will try to address. That will be very
Okay.
interesting. Even if I get the opportunity, I will definitely I'll be happy to do that.
Yeah, then it will complete now, actually if we do one frame structure,
Yeah,
three story or something.
exactly,
Yeah.
because we did, we have done beams, we have done columns, we'll be doing slabs also. Yeah, we can explore that possibility.
Okay. Thank you.
Yeah, thank you so much.